Hi guys, welcome back to the channel. So today we are going to be solving weekly contest fourth question, which is find the edges in the shortest paths. So we are given an undirected weighted graph which will consist of n nodes, and then this will be numbered from 0 to n minus 1. And then we are given edges where it will have ai and then bi and then wi, which will represent the two nodes which are present in this particular edge with this particular weight of wi. And then we need to return answer I as our answer, which will consist of, suppose let's say this will be of length edges of I dot length. And then we need to make sure that we need to find all the shortest paths which will start from 0 and then it will end at n minus 1. And then if this particular edge is present, if this particular edge is present in the shortest path, then we are going to mark it as true. And then if that particular edge is not present in the graph, then we are going to return as false. And then at last we are going to return the answer. So let us take this particular example where we have 0 and then 1, this particular graph. So we need to find all the shortest distances. So it is going to be 0 1. So this is going to be our paths. The first path is going to be like this, and then second path is going to be like this. And then if we come to the third path, we are going to take this one, and then again this one, and then again this one, and then again this one. So these are the three paths which we are going to have. One is from 0 to 1 and then 1 to 5. The second path is from here to here and then here to here and then here to here. So the distance is going to be 5, but the paths is going to be like these paths. So we need to find the distances from 0 to till all the elements till we reach this particular destination, which is 5. After finding the destinations, we need to find the edges which are involved in this particular path. Suppose let us say we'll calculate the distances of this particular nodes from from this particular source. Suppose we'll take it as 0, and then I'm going to use 𝗪𝗏𝗃 algorithm where it is going to pick all the adjacent elements and then it is going to push into our priority queue based upon the distances. And then we are going to pick with the smallest distance and then we are going to traverse again. Suppose I'll mark it as 0 as of now, and then for 4 I'm going to mark as of now the distance is going to be 4, and then for this it is going to be 1, and then for this it is going to be 2. I'm going to push 2 and then 1 into the priority queue, and then I'm going to pop this out, and then again for this I'm going to push 3, and then for this I'm going to push this one as well as this one, but the distance is going to be 6, and then the distance is going to be 7 for this, so we'll not be taking that. But if I see here to here, the distance is going to be 4, so I will push the 4. But suppose after coming here I'm going to push again 5, so this is going to be distance of 5, and then again this is going to be the distance of 2, and then again we are going to push it as 3, so it is going to be 5. For this it is going to be distance of 7. Now we got all the distances between source to this particular destination. Now we need to find all the edges which are involved in this particular shortest distance. So for that we'll start from the destination. After starting from the destination, I am going to take the distance of this particular node plus this particular weight, which is going to be this node should be equal to this destination node. After getting this node, I'm going to push into my queue, and then for this also I'm going to push this particular node into my queue. After pushing this, I'm going to check again this distance is going to be uh, distance of this adjacent node plus weight or not. If it is same, then I'm going to push again into my queue, and then I'm going to check again. Suppose let's say I have found this node, and then I visit this particular node, and then after this I am going to come here and then if I see the same distance, I will not be pushing again into my queue. Why? Because this node is already visited. That means it is going to consider all the edges which will have this particular shortest distance. So that's why we are going to include the visited array as well. And then we are going to return this particular answer as our answer, and then we are going to return answer. So let us see the code for this. So first we are going to take adjacency list, where it is going to store the node, adjacent node, and then the weight, and then we are going to take the answer, and then we are going to need the index which will which will do the which will have the map where we'll have a vector of two nodes, and then it will show us the index of this particular edge. And then we are going to have the visited for traversing between from destination node to till the source of this particular node. And then I'm going to have the distance for each node. I'm going to traverse through each edge which is present in this particular graph, and then I'm going to push this particular edge node, adjacent node, with the weight. And then for this it is going to we are going to push adjacent node and then wait, and then we are going to mark this as index I for this particular nodes, which is going to be v of 0 and then v of 1 and then v of 1 to v of 0, and then we are going to increment the I. And then we'll start from the source distance, and then we are going to mark it as 0, and then we are going to take the priority queue. Why? Because this is a weighted graph, so we need to pick the distance where it has a minimum, it should have the minimum distance between source and then the particular node. So that's why we are going to take the priority queue, and then first is going to represent the weight of this particular node, and then second is going to represent the node. And then till the pq dot empty is uh, till pq becomes empty, we are going to traverse this particular priority queue, and then we are going to pick the node, and then we are going to pick the weight, and then we are going to pop this particular node. And then after this, suppose let's say this particular weight which is present as of now is greater than the distance which we had found as of now. Like suppose let's say I have the four distance, suppose I have four distance. Now let's say I have one more, like here one more node is present which is 1. Now I had pushed this 4 comma 1 into my priority queue. Now again we got one more node from 2, which is going to be 2 comma 4, 2 comma 1, which is going to have the distance of 2, but it is going to have the node of 1. Suppose if we anyhow find this particular distance which is greater than this particular distance which we have right now, at that time we are going to say that it is not a valid answer, so we are going to continue. And then if we find this particular node which is destination, at that time we are going to stop, and then for each time we are going to see the adjacent node of this particular node, and then we are going to calculate the distance of this particular adjacent node. If the distance of this particular adjacent node is greater than the distance of node plus weight which is present in this particular edge, then we are going to say this this node is going distance of this adjacent node is going to be distance of node and then weight, and then we are going to push into our priority queue, and then this will calculate us the distances from the source to destination, and then it is going to have the shortest distance which is present. And then from now we need to traverse from destination, that means from 5 to till all the nodes which are present. So for this we are going to visit this one, and then for this we are going to visit this one again, and then again this one, and then again this one, and then we are going to mark those. So we are going to take the queue, and then it is we are going to push n minus 1, and then we are going to pick each node, and then we are going to find the adjacent node for this. And then if this distance of this particular node is equal to distance of this adjacent node plus y, that means this particular edge is existed in this particular shortest path or not. If it is existed in this shortest path, if it is not visited, then we are going to push into this particular queue, and then we are going to mark this particular index as we are going to contain in the shortest path, and then we are going to mark it as true, and then at last we are going to return the answer. Yeah, that's all for this video. Thanks for watching the video.